So good morning, all of you. So if at all someone can confirm that the screen is visible and I am audible, that would be great so that I can start. Am I audible? Okay, thank you for the confirmation. And the screen is visible to you?
Yes, sir.
Okay, thanks a lot. So we will start from where we left. So we were doing TDM, I think we were studying. This is important from the perspective of exam as well as from the perspective of general understanding, because at least after doing a course in digital communication, we must know that how do we really multiplex different signals, because this is one of the hearts of making communication accessible for all. Okay, because if we cannot allow simultaneous transmission, or if we cannot give the facility simultaneously to multiple people, then it is not useful. Okay, it means if at all I have a mobile phone and you also have a mobile phone, then we both should have the chance of calling at the same time. It's not that somebody would allocate us some slot to call. Okay, so this is basically done using the concept of multiplexing. So we were building some sort of a base for it in our last class. Okay, so I think I was discussing this T1 system. So let me just again write instead of discussing. So this is our today's lecture. This is lecture 13. So today the agenda is to discuss the remaining things of TDM and to discuss the spectra for line codes. I think this was missing. I didn't do it, assuming that first we will cover autocorrelation functions, some random processes, and then we should do it. But after talking to Professor Godgaonkar, who teaches section B, I found out that at least I should introduce the concept of the spectra of those line codes. So I will be doing that today. And whatever remains, let us say if you are not able to understand this autocorrelation function or these things, then once we go ahead and discuss random processes, then we will get to know it. Okay. So let us say for the purpose of TDM, time division multiplexing, what you do is that suppose you have n message inputs. Okay, suppose you have n message inputs. Okay, and then you restrict in bandwidth all of them, all of these, whatever you call, by a low pass anti-aliasing filter. Why this is required, I think we have already discussed, because of the time limited, band limited concept. And secondly, if at all we do not band limit it, then we cannot determine the Nyquist rate easily. Okay, once we band limit it, then it's easy to say that the Nyquist rate will be greater than at least twice of the bandwidth, or equal to, if at all there is no sinusoidal function in the signal. Okay, because they lead to impulses towards the end of the spectrum. I think I discussed it when we were studying the sampling theory. Okay. So you restrict it by an anti-aliasing, by low pass anti-aliasing filter, where W is the cutoff frequency. Okay. So W is the cutoff frequency for this filter. This won't be an ideal filter. This would be definitely having some leakage, but we can have a better design where this leakage can be minimized. Okay. Now we introduce a new device. We have to apply it to a commutator. Okay. So what is the purpose of this commutator? We will see. And this is usually implemented using electronic switching circuit. Okay, switching circuit. And now what it will do is it will sequentially interleave these n samples inside the sampling interval. This is very much to understand that we have kept the sampling interval as T of S, which is determined by this W. Why? Right now what the TDM system we are studying is that we are limiting each of the n input signals by a bandwidth W. It means all of them we are assuming will be sampling at a common rate. Okay. So this is, first of all, we are discussing such a system. Inside the sampling interval, TS. Okay. Now, final operation what you will do is, now you will pulse modulate. Now, what is the meaning of pulse modulate? That let us say you have the sample and then you will basically encode, or right now in the PCM system you will be encoding it into a bit sequence, and that bit sequence you will pulse modulating. It means you will be representing those bits in the form of a waveform, and that we have studied that there are several possibilities, at least 5 possibilities we studied. That is unipolar, bipolar, RZ, NRZ, Manchester. Okay. So today we will see what will be the ultimate spectrum of these coding techniques. Basically, what is the purpose of coding technique, or line coding, or you can pulse modulation of the bit sequences. You have the bit sequence, but ultimately to transmit it to the other end, whether you use baseband or passband. It means whether you are transmitting the waveform as it is, or you are modulating it to some higher spectrum. In both the cases, you first need a waveform of that 010101. Otherwise, that is a data. You cannot transmit data as it is. You need to have some signal which will ultimately be used, because you have hardware circuitry to work with. You have antennas and you have all these things. You have wires. So over wires, how will you transmit 101 unless you have a waveform? Okay. So then pulse modulate and transmit. So these 4 are the basic operations which we do in a TDM, time division multiplexing system. Okay. So now let us see what is. Let us suppose there is a, you can say, a switch type of a thing which is revolving. Okay. And let us say it has 2 terminals. One is this and one is this. We are assuming that we have 2 message sources. This is message 1, suppose, and this is message 2. And this is some sort of, you can say, a circuit which allows you to take sample of message 1 and then sample of message 2, then sample of message 1, then sample of message 2, and this goes on. Okay. And this is revolving. This is basically a commutator. Okay. It commutates several things and gives one output. So let's say this is your output. So this output will have, let us say, sample 1 for M1 message 1, then sample 1 for message 2, then sample 2 for message 1, then sample 2 for message 2, and this goes on. Okay. Suppose we are assuming that we have only 2 message sources. Now the point is that the gap between this and this is T of S. Okay. It means, let us say, if the sampling rate for this was twice of W, and the sampling rate for this as well was twice of W. Okay. So if at all this is your sampling frequency f of s, then the sampling interval is T of s, that is 1 upon 2W. Quite simple, we have already done it in the sampling theorem. So the gap or the time interval between the appearance of the first sample and the second sample is T of s. Now within T of s, I am putting one more sample here. That is, this sample is for message 2. The same is happening here. So there are 2 interpretations for it. One is that the gap between these 2 samples is also T of s. अब इसका इम्पैक्ट क्या है? सपोज अगर हम इसके अंदर n बिट का वर्ड यूज करते हैं, if we use n bit code word to represent after quantization, but to represent samples. Then earlier without TDM, you had TS. You can say you have TS time to stuff n bits. Okay, this is quite simple to see, because there was one sample, then another sample was coming in TS time. So I have TS duration. I can then put n bits in between. बेसिकली अगर 0 1 0 1 1 1 करके n बिट का सीक्वेंस है लेंथ का, सो हर बिट को मेरे को मतलब टोटल टाइम जो ये पूरा सीक्वेंस लेना चाहिए वो t ऑफ s लेना चाहिए, क्योंकि इस t ऑफ s के बाद अगले सैंपल का बिट सीक्वेंस आ जाएगा। Quite simple to understand. So bit interval कितना हो जाएगा? T of s divided by n. यानी I can give only this much amount of time to each bit. Ts upon n. So if I need to use a pulse to represent this 0 or 1, that pulse has to have a duration or width of Ts by n. Okay. So pulse width. Basically I should write what I am speaking so that it's clear once you go through the notes. If at all you are interested in going through it. So pulse width slash duration for each bit is this. Okay. Now the problem comes when you have TDM. Once you have TDM, now for combined 2n length, suppose now you have 2n length bit sequence with TDM. Okay. So effectively your bit interval or your pulse width has to be reduced, because after TS you need to get the same thing is repeats. Okay, so effectively the bit interval is now TS by 2n. So this is what is, let us say, you can say ऐसा नहीं है कि everything comes without any cost. So if at all you have this TDM principle, then it is leading to reduced bit intervals. Now the problem is I can relate it to one important concept. If I see the rect function, okay, and if I see its Fourier transform, or let us say a tentative consumption in the frequency domain, so we know that it's the standard sinc function. Okay, suppose it's the sinc function. But you will realize that the width of this central lobe, or the main lobe you can say, is inversely related to this width. Okay. If at all this is very short, this will be wider. Okay. So that is happening. तो इस केस में अगर कम बैंडविड्थ कंजम्पशन था, तो इस केस में ज़्यादा हो जाएगा. तो ऐसा नहीं है कि हम लोग अगर इंटरलीव कर पा रहे हैं या हम लोग TDM कर पा रहे हैं. See, one more thing I need to say at this point, that if suppose I sometimes shift to Hindi in between, if there is someone who is not very comfortable with the language, then you can definitely just unmute and say, so that I shift back to English. I sometimes shift to Hindi, assuming that a few concepts may be clear in some other language than English. Okay. So that is what I am saying. If at all the width, the pulse width is very short, this increases. Okay. Inverse relationship. Inverse relationship. Okay. This you can easily see once you. I think we have seen this several times. This Fourier transform expression. I think this is standard. If you see the Couch's book, it is this pi of t upon the width. I think this is the standard you read. And then this is sine of pi ftb upon pi ftb. All these things you can easily see from any textbook. Inverse and notes as well. So I think when you were discussing PAM, pulse stop, and all these things, so there I think you wrote this down. So because of this phenomena you will observe. So we will write this down. Okay. So TDM introduces a bandwidth expansion factor n. Now what is this n? N is the number of messages you are interleaving. So I gave an example with n is equal to 2, hence TS by 2n happening. If at all you are using some other number of users, the 3, 4, 5, so your TS by capital N into small n will be the this bit interval. Okay. Because the scheme must squeeze n samples derived from n independent sources into into a time slot. So time slot equal to 1 sampling. Okay, that I think I have clearly explained about. Okay, I think we can see one figure from the textbook. Let me just find it out for you and I can project it here. Okay, yes. So let us see our Haken's textbook. I think I had. So this is Couch's textbook. Let us see the Haken's textbook. Okay. So this is. Yeah, so this is the figure I think which we should see very clearly what is happening is. So we have, let us say, message inputs 1 to n, capital N message inputs are there, capital N number of message inputs. You have a low pass anti-aliasing filter, and then you apply each of the message inputs to the commutator. Now commutator is what? It will just rotate, basically a type of electronic switch होता है. देखिए, whatever scheme you design, it's, if at all it needs to be used somewhere, then it's entirely dependent on the hardware circuitry. And ultimately, the performance of these systems are definitely limited by the performance of the hardware. So you need to have such a switch which can really basically interleave such n samples, okay? Or you can say these n inputs को interleave कर सके, सबके बीच में commutate कर सके, ठीक है? So let us say this is a switch which is being done. As right now our course is more on understanding the concepts than to study the hardware. So we assume that there is an electronic switch which can do this. So that is called as a commutator, and this is just rotating at some frequency which you set. So right now we set it as T of S. It means it will basically you can say कि जो twice of W है उस rate पे घूमे, so that it return backs to the same place after T of S seconds. Okay, that is what will happen. Then ultimately after the commutator, so this here you will have a bit stream type of thing. Here you will have a bit stream. Then you pulse modulate it. There is a communication channel. Then pulse demodulate it, and then you have to distribute the message inputs among their probable outputs. So एक type का जो system हुआ कि let us say there is a colony in which you have 300 homes, and from each of the home there is a wire which goes to some let us say a box installed at the entry of the community. Okay, so 300 wires now are put up into a single wire which goes to the exchange. Okay, this is like this. At the exchange, this single wire, from this single wire, again, each of the let us say signal for 300 houses is separate out, and then it is analyzed, or it is connected to the whatever the billing system or whatever. So this is what. Now this is synchronized. Now this is a very you can say the heart and soul of this TDM system, because you must be synchronized. Otherwise, what will happen? Sometimes you will deliver the message, let us say for source 2 to source 2 if you are not synchronized. Okay, it means you need to know where the pulse starts. Let us say if I say the pulse starts as T0, so here also at T0 I should sample for message 1. And then after T0 plus TS, I should go for message 2. So T0 plus TS, I should go for message 2. If by chance this T0, I do not know where the pulse starts, then I can randomly assume that whatever bit I get is for message input 1, and maybe it is for 2. So this is the heart and soul of the TDM system. You need some way to synchronize your commutators with the transmitter and receiver. And for this, you do a lot of things. Okay. Specifically, you will put some synchronization bit which will allow the receiver to know where the sequence starts and stops. The problem with us right now in studying TDM is that we do not have that much of time to give to TDM, because we have several topics and otherwise to cover. So I wanted to cover this synchronization design, but I don't think that much time is there with me. So synchronization, I just told you that there is a bit which we had. I think here we use when T1 system I was explaining in the last lecture. So I used one here. We use one more bit for synchronization. I think that is what it is written here. Now this synchronization bit helps both the commutators to have a common sampling time. ओके मतलब इंस्टेंट्स फिक्स होने चाहिए कि अगर टी नॉट पे इफ एट ऑल एट टी नॉट योर मैसेज वन स्टार्ट सो एट द रिसीवर इट शुड अगेन स्टार्ट एट टी नॉट, अदरवाइज व्हाट विल हैपन, अगर आपने गलत सैंपल किया तो आप मैसेज फ्रॉम सोर्स 2 you will deliver to message from source 3, okay, and then this is the popular term which is called as crosstalk. And not because of this but because of the problem with the wires, if at all you remember, I don't know how many of you used to have MTNL or BSNL telephones in your home, maybe because they have now been obsolete, mostly, okay. So there sometimes let us say we are talking and you will listen to the basically the chat of someone else as well, maybe your neighbor or somebody else, you will get to listen, okay, because I have personally experienced this when we were kids, so this used to happen often in BSNL and MTNL telephone lines, okay. Nowadays it doesn't happen, I think, in the Airtel lines and all these new broadband techniques which deliver telephones simultaneously, okay. So here let us see one more important thing, that earlier we were having the sampling rate of 8 kilohertz for one of the channels, let us say for one of the message sources 8 kilohertz, but and if at all we use 125 microsecond was the bit interval available. Okay. I think, yeah, 192 bits. So then it has reduced to 0.647 microsecond. So you can see that the transmission rate has increased, but the bit interval has reduced. This reduced bit interval will lead to a higher bandwidth consumption. Now this imposes a problem to the wire transmission. Okay, let me write it down. So the bandwidth increase now requires the system to clean pulses at regular intervals. Why? Because जो wire का frequency response है, suppose let us say this is the coaxial or this is the two wire cable which you use supposed to transmit this. So this wire may not have a frequency response which is quite, you can say, acceptable for the frequency range which we have now generated. Because of interleaving of these n independent sources, our bandwidth consumption has increased by a factor of n. So हो सकता है कि suppose इसका response ऐसा है और ये सिर्फ इतने से इतने तक स्ट्रेट है, बाकी पे ये शार्पली फॉल कर रहा है सपोज. नाउ वी हैव इंक्रीज आवर बैंडविड्थ कंजम्पशन टू दिस. नाउ व्हाट इज हैपनिंग इज दैट द कंपोनेंट्स इन दिस फ्रीक्वेंसी रेंज are now attenuated as the that signal is propagating. So what we have to do, we have to put a repeater here. So this repeater will take the pulses again, let us say generate them, that is called as fresh pulses it will generate and then transmit. तो मतलब बीच में आपको अटेन्युएशन को हैंडल करना पड़ेगा. कुछ अटेन्युएशन भी होगा केबल के अंदर, वो तो क्वाइट ऑब्वियस है, बट फ्रीक्वेंसी रिस्पांस की करेक्शन भी आपको करनी होगी बीच में. एंड दिस इज अ चीप ऑपरेशन टू डू because of the cheap hardware circuitry. That means the system has evolved such that doing like this was more or less feasible, and in the system which was initially installed for telephone communication had these boxes there. Okay, तो उसी बॉक्स को थोड़ा बड़ा करके उसके अंदर रिपीटर्स लगा दिए गए, तो आसानी से इस सिस्टम को यूज किया जा सकता है. टीडीएम इस तरीके से पूरा टीडीएम इंप्लीमेंट हुआ है. इसमें कई सारे एस्पेक्ट्स हैं. So we have seen, at least हम लोगों ने what we have done is that in short we have seen what TDM is. So I think we have seen one of the diagrams for TDM. Let us now move ahead and see what is remaining for us to study in TDM. Okay. Let us see one more thing. Let us see one example for it. Okay, and for this we will use Couch's book to study this. So up to now what we have done is that we have studied, you can say, a system which has a common sampling rate. But this TDM, I think you can see this. Let me just zoom in more. Yeah, now. So up to now we have done, let me write it down. So up to now we have discussed TDM for message sources with common sampling rate. Okay, that is what the photo I showed it to you from Hicken. Common sampling rate. Okay. What about multiplexing? What about multiplexing sources with different data rate? Okay, data rate I am saying because let us assume that whatever messages we have streams of bits. Okay, 101010. Now let us, क्योंकि सपोज आपके घर पे एक लाइन आ रहा है, उसी में आपको वॉइस भी लेना है और उसी से आपको डेटा भी लेना है. I don't know if you remember, there used to be a PSTN type of a system in MTN or BSNL where you just use a modem, then it used to dial your number and from that you can use internet. So on the same line, let us say the two wire line, which was standard two wire line, which was coming to our homes, used to deliver voice as well as data. Now the problem is that both of them have a different sampling rate, or the rate of bits are different in both of these systems. Let us say each will have a different bit rate. Okay. Now how do you multiplex this? Let us say if this is coming at a different bit rate, this is obviously will be at a different bit rate, because most of the voice systems will be using an 8 kilohertz of sampling rate, and it will generate a fixed bit rate, and data may have a higher bit rate. Let us say if you are using viewers watching video, or you assume, you know that for data there is no fixed data rate and it will vary. It can be very high, very low. Let us say if you are transmitting files, it can have a low data rate, but if you are transmitting videos, it need to have a higher data rate. So, and if you are live streaming, then again the data rate requirement is quite high. So for this, there is an example, very good example given in Couch's book, which I just thought of discussing, so that you know that ऐसा नहीं है कि TDM में एक ही पॉसिबल चीज है कि आप सेम बिट रेट के सीक्वेंस मैसेजेस को कैसे मल्टीप्लेक्स करते हैं, बट इट इज that how you multiplex different data rate sources. So suppose assume that there is a source 1 which is analog signal and it has a 2 kilohertz of bandwidth. There is a source 2 which is analog, but now it has a 4 kilohertz of bandwidth. Okay. And then there is a source 3 which is analog, 2 kilohertz of bandwidth. And there are, let us say 4 to 11, 4, 5, 6, 7, 8, 9, 10, 11. So 8 sources, and each source is digital. It means, let us say there is data, files, whatever. And it is generating, each source is generating 7200 bits per second. Now these, let us say 8 plus 3, 11 sources you have to multiplex. Okay. So ये 11 signals हैं आपको एक साथ multiplex करने हैं. अब इसको आप कैसे solve करेंगे? Okay. So I think we will go through this explanation which is written, and then we will simply see this diagram for our understanding. Okay. And then we are done with TDM. Okay. So you know that if I try to find out the Nyquist rate for the sources, so for source 1 it has to be 4 kilohertz at least, for source 2 it has to be 8 kilohertz, and for source 3 it has to be 4 kilohertz. Okay, so first of all let us deal with the analog sources. First of all let us try to you can say multiplex these 3 sources. So let us see. Okay. How do you do that? So let me write example. So we are discussing, let me just see what is the example number 36. Okay. So example 36 from Couch we are discussing. Couch 2's book. So source 1, let us say is 2 kilohertz is the bandwidth. So Nyquist rate NR, I should not write NR because then maybe you won't remember that this is Nyquist rate. Nyquist rate, which we now call NR, is 4 kilohertz, means you have to sample it at a rate which is greater than this, then 8 kilohertz. And then there is source 3 which is again 2 kilohertz. So Nyquist rate comes out to be 4 kilohertz. Now the question is that let us first study the multiplexing of these three analog sources. Three analog sources. How do you do it? So that is the question we need to, or we are interested to study. Now one option is that you sample S1 and S3, both of them at 8 kilohertz, bring the sampling rate at a common point, and then you multiplex. But this increases your system complexity unnecessarily. See why? Why should I sample at a very high rate S1 and S3 when that is not required? And I may have a pretty much acceptable recovery even if I use a 5 kilohertz sampling rate. Means ठीक है, नाइट्रोस्टेट से थोड़ा ज़्यादा कर लेते हैं, ज़्यादा करना हमारे लिए it's better for system design, for studying it, and for implementing several things. But then why to unnecessarily go to it? So this is a question that means it's very hard to think that we should increase the sampling rate. Okay. So the way out is, if at all I am collecting one sample from source 1, okay, and then let us say this is sample 1, and this for source 1 itself sample 2 comes here. So in between, let us say this is 4 kilohertz of it, okay, at 4 kilohertz. And if I try to stuff in two other sources in between, it means अब source 2 और source 3 को बीच में डालना है मुझे, तो अगर मैं source 2 का एक sample डालता हूँ बीच में, if I put one sample for source 2, then if another sample for source 2 comes at this, then I can definitely give it a 4 kilohertz sampling rate as well, because now the gap between these two samples will be according to 4 kilohertz. Okay, means दोनों का जो nyquist rate है मैं इस तरीके से satisfy कर सकता हूँ. But एक problem है, if I try to give source 3 only one possible sample here and the second sample appears here, then effectively this is also getting only 4 kilohertz of sampling rate, which is not at all acceptable, because this won't lead to recovery at the receiver. So what to do? So the idea is, instead of collecting one sample for source 3 in this interval, let us collect two samples of source 3 in this interval. Okay. So the possible arrangement is that for source 1, if I am collecting first sample, at least this is 1 point, and this is the second sample for source 1. So suppose I first collect first sample for source 3, then I collect one sample for source 2, and then again I collect one more sample for source 3. So now within this 4 kilohertz of, let us say, gap, or this is just I am trying to explain, I am not putting it the exact T. T जो आएगा 1/4 आएगा, तो आप 1/4 T put करके इसको और बेहतर तरीके से you can understand. So within this same 4 kilohertz, or the rate which will come through this 4 kilohertz, I have collected two samples. So effectively, I can now give 8 kilohertz of a rate to source 3, maintaining my commutator at 4 kilohertz. Okay, मतलब मेरा जो commutator है still 4 kilohertz पे था, but मैं S3 को 8 kilohertz का sampling rate दे पा रहा हूँ. अब उससे नेगेटिवली क्या हुआ कि अगर इस ड्यूरेशन में 4 किलोहर्ट्ज की, if I was using only 3 samples, so my bit interval was, let us say, TS by 3, मतलब by 3 से डिक्रीज होता, बट अब by 4 से डिक्रीज हो जाता. बस this is what is the main point behind multiplexing several signals. So you need to effectively give the required sampling rate by efficient stuffing, and that is what, let us say, what this does. So if you, I will just zoom in more. So now let us see. So what is happening is, if you just see from source 1, from source 2, and from source 3, you just see these three inputs. Okay. So one is 2 kilohertz analog, another one is 4 kilohertz analog, and this is 2 kilohertz analog. And this is the commutator, which is now revolving at a rate of 4 kilohertz. Okay. So you see that source 2 has two inputs now. So this commutator first will collect one input from source 1, then from source 2, then from source 3, and again from source 2. So in a cycle, it collects one sample from source 1, one sample from source 3, and two samples from source 2. Okay, and this will ultimately lead to 16 kilosamples per second. Now why? Because we are using 4-bit PCM word. So it is given in the question. It also assumes that the analog sources will be converted into 4-bit PCM words. So if each source is using 4-bit word and I am collecting 4 samples within let us say 4 samples in one revolution. So each sample, if it has 4 bits, so 16 bits will be generated in each cycle, and it is having 4,000 cycles. So that is, I think, the 16 kilosamples per second comes. Then you will have 4-bit A to D converter. Okay. So I think this is further you can study here, that how do you then put it up with the remaining 8 sources. Okay, and this would be now easier for you to study. I assume this should be now easy for all of you to follow. This is I would say important from the perspective of understanding TDM properly. But if at all you are even able to understand partially, so this is also good. It means it depends on your own study. अब ये जो आपकी बाकी बचे 8 सोर्सेज हैं, that is 4, 5, 6, 7, 8, 9, 10, 11, each will have a common rate, that is 7.2 kbps. अब एक concept है pulse stuffing का. Why this pulse stuffing is used? That sometimes to have uniformity we want to increase the sampling rate. So इसका 7.2 kbps को आपने 8 kbps में convert किया, dummy pulses डाल के, dummy bits बीच में डाल के. So let us say you convert each of this source to a standard, let us say 8 kbps, and now you have to design another commutator. Now this commutator, what it will do is, now it will just, let us say this is one of the possible bit sequence which is coming because of multiplexing 3 sources, and now this bit sequence will be multiplexed with these 8 bit sequences, and ultimately the output would be 128 kbps. Okay. The full explanation is written here. If at all you understand what I have drawn here, what I have written here, then it should be, I think, easy. So if at all you have any comments to make on this, then you are most welcome. You can just go through and read it. I think the midsem exam is very, very nearby. If you have gone through it, then it's good. If you have not, then please do go through it. This is a very simple system. Only one example which I have discussed in this class. I am not discussing this commutator because I don't know if this concept is very clear or not. So I am leaving this for self-study because I assume if this is clear, then understanding this is also very clear. I basically, that's why I just discussed the first part. I'm not discussing this because few things should be homework so that you enjoy reading. Okay, so half of the things I have explained, half you can try to do it on your own. And as I always say, that if doubts persist, then do inform me. We can have a separate session to discuss. Okay. So now we will come to the concept of line codes. That is what we need to do today to complete our course for, or whatever our part for midsem. So this line codes we have done already, but we have to do the spectra. So I am just doing it. So I am not doing some derivations. Why? Because as I already mentioned, that we do not have that much background of random processes. So we will just use the results. Okay. So let me just write it down. So a digital signal, let us say कि एक सीक्वेंस है जो आपको दिया हुआ है और उस सीक्वेंस से आप एक सिग्नल जनरेट कर रहे हैं, तो उसको हम कैसे रिप्रेजेंट करेंगे? तो अ डिजिटल सिग्नल मे बी modeled by x of t is equal to summation n is equal to minus infinity to infinity a of n f of t minus n t b. Where what is a of n? Let me write it down. So a of n is set of random variables, that represent the binary data. बाइनरी डेटा. ओके, मींस अगर आपके पास सीक्वेंस आ गया बाइनरी डेटा का 1010 की पूरी स्ट्रीम आ गई, अब उस स्ट्रीम को जब आप एक कन्वर्ट करते हैं एक सिग्नल में, बिकॉज करना ही पड़ेगा, नहीं तो ट्रांसमिशन कैसे करेंगे उसका? तो फॉर दैट आई एम रिप्रेजेंटिंग दिस conversion or this process of making a continuous time signal out of it is, you can easily write in this form. So I am explaining what it is. And f of t is the signaling pulse. Okay, is the signaling. We should have a double L. Is the signaling pulse. The pulse shape, and TB is, and TB is the duration of 1 bit. TB is the duration. सो आप क्या कर रहे हैं एसेंशियली, जैसे कि आपका 0 1 1 1 0 0 1 1, suppose this is the bits which coming. So if I am, let us say this is my pulse, if I am using this as the pulse shape, I can obviously use, let us say, this also as a pulse shape. I can use the same function also as a pulse shape. So I am multiplying it with this and adding all of them with shifting. So suppose, let us say, if this comes at this point, then I shift this pulse by t of pp. Let us, this is my TB, this is my TB. Okay, so I shift this pulse by TB, so I will get, let us say, by this. So I am shifting these pulses by TB continuously, and I am multiplying each of them. So if at all this is the case, then I will have 0, then I will have 1, then this 1 stays up to this point, and then let us say this is 2 zeros and then 2 ones. So this process I can write, let us say if this is the waveform, then I can write it in this form. Summation from going from minus infinity to plus infinity, the A of n, that is the speed sequence, and multiplied by the shifted pulses. Now this is why we are doing this, is because the concept of pulse is quite obvious, because in hardware you can tackle each bit individually, and you can have time limited pulses. That is the only possibility which you can generate, time limited pulses. So that's why this concept of shifting and then multiplying, this is called as a linear modulation. Why? Because this waveform is generated out of scaling and adding. Okay, so this is, there are two operations which define this linear, I think, transfer function or whatever you have gone through in signal system quite well. So you must relate. Okay, if that is the case, then how do you, if so, so this way you can represent your each of the line codes. We will see how to do it. So let Rk, I am representing, I am writing from here. So let Rk denote the autocorrelation. Denote the autocorrelation of the data given as R of k is A of n plus k bar. Okay, now this bar I am telling what it is. So this is equal to summation I is equal to 1 to capital I A of n plus k I P of I. Okay, what is it? Let me tell you. So P of I is the probability. P of I is the probability of getting the product. Probability of getting the product A of n into A of n plus ki, of which there are I possibilities. Okay, so if at all you remember this formula, then you can derive the power spectral density of any line code. So I am not at all discussing the basically the way you come to this formula, because until and unless I have discussed some concepts of random processes, there is no, I think it's not good to discuss this. So that's why I'm just giving you the formula. You can just apply the formula and get the power spectra. Very simple. Okay. So for such a sequence, let us say I can evaluate the PST. So PST of x of t is given as, now PST I assume you may be knowing, although this also comes from random processes, but what to do. I can just simply quote the word right now. So P of x f, that is this x, the signal x of t, which is given by this equation or this expression, you can say. This is given by the square divided by ts. ts is the symbol in interval. Here it will be tb. ts will be equal to tb because हम बाइनरी मॉड्यूलेशन कंसीडर कर रहे हैं, मतलब बाइनरी हमारी बिट स्ट्रीम, वी आर नॉट कंसीडरिंग सिंबल्स, ओके, which you I think must have seen in your introduction to communication systems course. R of k e raised to power minus of j k omega t of s. So this is a very simple formula for obtaining the power spectral density of any signal which is represented in this form. Okay. Now let us see what is f of f and all these things. So f of f is spectrum of the pulse shape. Okay, spectrum of the pulse shape of the digital symbol. Means whatever pulse you are using, what is, suppose let us see one thing. जैसे कि अगर आपने यहाँ पे रेक्ट फंक्शन यूज किया है द पल्स शेप, सो व्हाट विल बी एफ ऑफ एफ, इट विल बी द सिंक फंक्शन. ओके, सिमिलरली अगर आपने थोड़ा स्मूदर पल्स यूज किया है तो जो उसका कॉरस्पॉन्डिंग स्पेक्ट्रम आएगा दैट विल बी द what you will place in here, and then you will take the absolute value in square, so this will come out to be a real quantity, and real as well as positive, you can say non-negative. Okay, ts is the symbol interval, but here which is equal to TB for only two possible symbols, 1 or 0. Okay, for this is TB for binary data, or input. I think I should write binary input because data, ultimately symbols also get converted from binary. Okay, TB for binary input. Or two possible symbols. So I think I will write one final thing, and then we can simply discuss the spectra of all the 5 you can say line modes. I need to write one observation. So from PXF you can see, oh sorry, first I think I need to write what is the quantity in the bracket. Okay, I should write that first and then I will write what is the observation, because I think this is missing. So quantity in the bracket is the DTFT. I think if you remember, so DTFT of the autocorrelation function. And if you remember that this is basically the power spectral density of the input random process. मतलब अगर हम इसको एक discrete random process बोलें, यानी A1, it is, let us say A-2, A-1, A0, A1, 2, 3, 4. So basically this is a discrete, you can say a sequence, and I assuming each of the quantities is a random variable. Okay, so for such a, see, that is why I was not very inclined to discuss these things, because unless you introduce these concepts, but okay, for the purpose of general understanding we can just bypass few things. So I am just saying, if at all you can relate to it, it's great. If you cannot, you can search and find it out, and still if you don't do it, then you just remember this formula. Okay, that will also suffice. So basically ये PSD है इनपुट की, यानी कि जो आपका बिट सीक्वेंस आ रहा है, तो बिट सीक्वेंस भी प्रोबेबिलिस्टिक है, जरूरी नहीं है जैसे आप एक वॉइस सिग्नल भेज रहे हैं और उसमें जो 1 zeros का रेशो आएगा, और जो आप एक मीडिया फाइल भेज रहे हैं उसमें जो नंबर ऑफ 1s and 0s आएंगे, वो बहुत डिफरेंट होंगे, तो स्टैटिस्टिक्स बदल जाएंगे। ऐसा हो सकता है किसी केस में कि यू हैव मोर वंस देन जीरोस, यू हैव मोर जीरोस देन वंस। ओके, इट मे नॉट बी कि द बिट सीक्वेंस हैज अ हाफ ऑफ प्रोबेबिलिटी ऑफ बोथ 0 एंड 1, कि अगर 10,000 लेंथ का सीक्वेंस है तो इट इज नॉट दैट ओनली 5,000 बिट्स विल बी जीरोस एंड 5,000 विल बी वंस. It may be that 7,000 are ones and 3,000 are zeros. So it means it will have a different probability of 1 and 0 appearing. So it all depends on what data you are. And secondly, there is a problem of correlation as well. It may be that the data, it is A1, A2, A3, A4, this sequence is correlated. कि 1 है तो थोड़ी देर तक 1 ही रहते हैं, 0 है तो थोड़ी देर तक 0 ही रहते हैं, क्योंकि इमेज में ऐसा हो सकता है. If at all in top of image where the intensity is slowly decreasing, so it will generate, the nearby pixels will be very correlated, so data which they generate will be correlated. So in that's why for handling such cases we have modeled this A of n as a discrete random process. Okay, and this discrete random process will itself have a PST, and that is this. Okay, so this can be referred to as the PST of the discrete time random process. I should write discrete time, because then if you go through the notes you won't understand what is D of t, dt. I should write it. Of the discrete time random process A of n. Okay, okay, so now the observation which I wanted to write is that PSD of the baseband signal, that is after, let us say, the signal which you generate immediately after having the bit sequence, this signal x of t signal is influenced by both the spectrum of data and spectrum of the pulse shape used for the line. Okay, used for the line. So this is quite easy to see. So basically जो आपने pulse use किया उसका spectrum that gets multiplied with the PST of the input discrete time process. Okay, so this is quite interesting to see that ऐसा नहीं है जो pulse shape use करेंगे उसी के spectrum को देख के आप easily comment कर सकते हैं कि कितना ultimately your waveform will consume. No, you need to know this PST as well if you need to exactly comment on it. Okay, but in most of the cases people even suffice that if at all f of f का consumption पता है आपको, तो वो कई बार कहते हैं कि that is a good estimate for the ultimate bandwidth consumption of this scheme. Okay, so let us start with the first scheme, that is unipolar NRZ. So उसको हम लोग study करते हैं. So first of all, that is unipolar NRZ. So let us remember unipolar is two levels, sorry, plus A and 0. So plus A is for 1, 0 is for 0. Okay, NRZ is it won't be returning to 0 in between the bits interval. Means TB के अंदर अगर वो plus A level maintain करता है तो वो 0 नहीं आएगा. RZ में half of the bit interval के लिए it comes to 0. Okay, or that time for which it comes to 0 can be customized, but we studied the line code assuming that that will be half. Okay. So let us say we find out for r of 0. Okay, let us say here we set r of 0. So अगर आपको देखना है कि an into an, so let me write it down. So r of 0 is summation I is equal to 1 to I, 0 to I, okay, 1 to I, a of n into a of n, p of n. Okay, So we have to check how many different we can have. A of n into, this is basically nothing but summation I is equal to 1 to I a n square and the probability of having. So let us find out what is I. So we'll have two things. One is a n can have two possible values, a and 0. So a n square will have two values. One is a square, one is 0. Okay. And since we have two values, and let us say if we assume that ones and zeros are equiprobable, if we assume, see, this is why we assume, for ease of obtaining some expression. Otherwise, I have already told you that it may not be valid for in a lot of scenarios. Okay. In order to make it valid, there are several things which are done. Okay, वो भी किया जाता है ताकि ये equiprobable हो जाए. So if we assume plus a and 0 appear with equal probability, that's 1 by 2. Obviously, you can assume. So this probability of having this will be 1 by 2, and for this as well as 1 by 2. So I becomes 2. So I will have I as 2. So I is 2 in this case. There are two things. And for k not equal to 0, suppose for k not equal to 0, that is R of k for k not equal to 0, this is simply given by, let us now we will find it out. So I go on to I, a of n into a of n plus k, which is I p of n. Okay. Now here k is not equal to 0. So we have, now we will have four possibilities. Why? Let us form a column. देखते हैं. अब k नॉट इक्वल टू 0 इसका मतलब है कि ये दो अलग अलग वैल्यू क्वांटिटीज हैं. ऊपर तो सेम क्वांटिटी थी, तो सेम क्वांटिटी दो ही पॉसिबल वैल्यू ले सकती है a, बट हियर वी विल हैव फोर possibilities. Let's say if this is a, this is 0, this is 0, this is a, this is a, this is a, and this is 0, this is 0. Okay, and the product is what? The product, if you do, that is a, so this is 0. Or I don't think that product, why to find a product, that is not basically required. There is no benefit of doing that because for our calculation it is not required. So we have four possibilities. So I comes out to be 4 in this case. Okay. So I is 4 and P of I is what? See, this, if this has a chance of 1 by 2, so this has a chance of 1 by 2. So this is 1 by 4. So now let us find out ultimately that what is R of K. So R of K is basically a square by 2 and a square by 4 for k equal to 0 and for k not equal to 0. With this as the expression of R of K, and you remember that for unipolar we are using this sort of a system. Let us say this is 1, this is 0 and this is 0 suppose, and then again 1 comes, so this is like this. Okay. This goes to 0 and this is the way. So this is a sort of a rect function. So f of t, जो pulse shape है वो rect function is standard. तो उसको हम कैसे लिखेंगे? T upon Tb. Why? Because what is pi of t? So pi of, this is 1, this is Tb by 2 and this is minus Tb. Now this pulse, this system we are going from minus infinity to plus infinity. Hence using this same, मतलब आप ये भी कह सकते हैं कि इसको आपने shift क्यों नहीं किया dB by 2 से? No, that is not required because the system we are analyzing from minus infinity to plus infinity. There is no concept of zero here right now. Zero कुछ मतलब आपका zero जो आप बदलेंगे कोई फर्क नहीं पड़ेगा. और दूसरी बात एक और है, अगर आप shift भी करते हैं तो यहाँ पे हम absolute value का square लेते हैं pulse का. This shifting will lead to a exponential term in the spectrum, and that will ultimately be squared and that we get to 1. Okay. So with this and using, so f of f is equal to Tb sine of pi f Tb divided by pi f Tb. Okay. And we use one relationship and using, see this is only one thing which I am writing, थोड़ा involved है, इसके बाद आपका easy है, पर बाकी सब waveforms का समझना. Why I am doing it is कि because Haken only mentions कि क्या effects, मतलब what are the issues with the frequency consumption of these 5 schemes, but it doesn't tell you कि how the spectrum is derived and why this happens. And that is very important for us as readers or students of the course. We need to know कि उसमें लिखा है कि मैं इसका DC लेवल होगा, वो आपको पता कैसे चला कि DC लेवल होगा? वो ऐसे पता चलेगा जैसे मैं कैलकुलेशन बता रहा हूँ आपको करके कि here you will, now we have really obtained the spectra and now we know that there will be a DC level in the waveform. Okay, so this is equal to, we are using this relationship basically, summation n is equal to minus infinity to infinity delta of f minus n by dp. Okay, बस ये यूज करेंगे आप. So I am writing it down that for p unipolar, that is the PST for unipolar R NRZ. Unipolar NRZ, f is equal to a square db by 4 sine of, I just plugged in the whatever I have written above into the formula which I have just given you a few moments earlier. 4 pi fp dp whole square into multiple. So I should write multiple. I should not use this flower type of an operator because this seems to be a convolution, into 1 plus 1 upon db delta of f. Now let us see this problem. Now this delta of f will take a non-zero value only at f equal to 0. So this clearly shows that P unipolar NRZ will have a non-zero DC level. Okay. So let us write the disadvantage of this. So let me write it down. So we have a finite DC level. Okay. And spectrum does not approach 0 near DC. Okay, this is it. So this is what I think this is mentioned clearly in, you can say, your Haken's textbook, that it has a finite DC level. I will explain that why this DC level is not very good or it is not very acceptable. Next we are discussing polar NRZ. So one was this unipolar NRZ, then is polar NRZ. It means you have plus A and minus A as the two levels, and the waveform doesn't return to 0 in the bit interval. Okay. For this, I am not doing that calculation. I am just writing the PST for this, so that the way I already explained. So you can just, I will be giving the reference from where you can get this. This is a square TB sine of pi f TB divided by pi f TB whole square. Okay. It also has a disadvantage that it has a large PST near DC. The near DC frequency, okay, that is f equal to 0. I should write it down, otherwise it is easy to generate, but requires two power supplies. Okay, but requires two power supplies, because one need to generate plus A and other needs to generate minus A. And there might be, it is said that there might be a sophisticated circuitry which can generate minus of A from plus of A. Okay, let me write it down. Unless a different circuit, circuitry which generates both levels from single supply. Now next comes the concept of unipolar RZ. Now what is this unipolar RZ? So in unipolar RZ, your waveform will return to 0 in between the bit interval. Okay, so here for I think should I display the unipolar RZ? I think you can. I have already shown it to you. Okay, then I will draw it. So 1 0 1 suppose. So unipolar फॉर्म है तो इसमें प्लस ए और जीरो दो ही लेवल्स रहेंगे, बट प्लस ए मेंटेन रहेगा हाफ बिट इंटरवल के लिए. So let us say this is plus a and this goes to 0 and then this is 0 and suppose this is then plus 1 and this goes to 0. So if this was your TB, then this is only TB by 2. So the waveform returns to 0 in during the bit interval. Okay. So here I think the pulse width. So we have obtained the expression. I think we have done the derivation for unipolar NRZ. So उसके अंदर क्या था कि unipolar क्योंकि प्लस a और 0 पे हमने जो वेवफॉर्म सिग्नलिंग वेवफॉर्म यूज किया था पाई t by tb यूज किया था, उसके अंदर tb by 4 होना चाहिए यहाँ पे, बिकॉज हाफ विड्थ का आपको यूज करना है, तो इसमें इट विल बिकम ट्वाइस ऑफ t by tb, मींस द विड्थ विल डिक्रीज. सो पल्स विड्थ और ड्यूरेशन is now TB by 2. Earlier it was TB. So you can see that the pulse width, the duration is TB, total is TB. But now it will be TB by 2. So for it to be TB by 2, here has to be minus TB by 4 to TB by 4. Okay. So directly I am writing that what is the expression you get for unipolar RZ as a function of frequency f. Let me see if I have used f here. Okay, I have used f here. So the expression which you get finally is, first of all, okay, let me write it down. So a square tb by, I think it is 16. Okay, maybe I have not written it clearly from the textbook. I will give you the reference anyways in the breakup file today. Pi f tb by 2 whole square and 1 plus 1 by tb into summation n is equal to minus infinity to infinity delta of f minus n by tb. Okay. So here you will observe that this unipolar RZ has several delta functions, and each delta function will appear at 1 by TB, 2 by TB, 3 by TB. Okay, so this is interesting. You will basically appreciate this once you will see the figure. I think let me show you the spectra of these line codes. I think they are yeah. So this is, I think this is given in Haken as well, but it has the author has not given you the expressions that from where do you get this. So you can see. So I said that in unipolar there is a impulse. Okay, so we found this impulse in our expression as well. Polar there was no impulse; it was only a simple sinc square function. So you are getting a sinc square thing. Here the author has only plotted it for positive frequencies. Definitely the spectrum will be there in the negative frequency as well. Now you can see unipolar alpha. So we have found out that there are impulse functions at 1 by TB. So 0, then R is 1 by TB here, then this impulses will continue. Okay. And then finally the two which are remaining is bipolar RZ and Manchester. So let me just write it down. So one disadvantage is first, null bandwidth. It means the bandwidth is increased. That is quite obvious because you have decreased the pulse width. So जो pulse width decrease करेंगे तो f of f जो है वो थोड़ा wide हो जाएगा. So first null bandwidth is twice. I explained this null bandwidth I think in 1 or 2 lectures before, where I said that the first time the spectrum touches 0. Okay, it's twice that for unipolar or polar signaling. Unipolar NRZ or polar signaling. Since pulse width is half as well. Okay. let me write it down one very important thing, that f of f is in this case TB by 2, so that those who are just referring to notes only, they can have a sort of a complete presentation at a single place. Okay. So then let us come to bipolar RZ. Okay. So then we have this bipolar RZ. Now here the point is bipolar means that you have plus A minus A alternatively coming for 1. 0 is for 0. You have 3 levels. Okay. So it has plus A and minus A alternatively for 1. Alternatively for 1 and 0 for 0. Okay. This was bipolar, I think, and it is a return to 0. So it will have plus A for half and then minus A for half bit time. So the expression for it is P of f is A square TB by 4 sine of pi f TB by 2 divided by pi f TB divided by pi f TB square sine square pi f TB. Okay. And the finally is Manchester. Let me just write it down. Manchester NRZ. So this is the last, you can say, line code which we studied, Manchester NRZ. Okay. Here the pulse shape. So this is very important. See, Manchester NRZ में क्या है कि half bit interval के लिए 1 होगा और I think बाकी के लिए it will go to a minus level. Let me check it out again. I think you can go back and see. This, here it is Manchester NRZ. Yeah, for half bit interval it is A, and then for another half interval it is minus A, and reverse follows for 0. Okay, so this is what the coding is. So f of t, the pulse shape, is very important to know what it is. So I won't be explaining this because this is very easy to find out from the concepts we have built in our simulation systems course, and I think explained this also in my course or in this course I think in the start. So this is the pulse shape, and the free spectrum which you get is A square TB sine of pi f TB by 2 divided by pi f TB by 2 whole square sine square pi f TB by 2. Okay. So this is what I have to say in this Manchester NRZ as well. So let us discuss one problem with bipolar NRZ. It has a spectral null at DC. This is a benefit. Okay. Spectral null at DC. Spectral null at DC. Now this is why problem is we use a lot of capacitors in the circuit. Okay. It means अगर आपको इस waveform को transmit करना है over the hardware, so you will be using capacitor for coupling and all these things. The problem with capacitors is that if you have a DC sort of a voltage, then they will just maintain that level. Okay, so they will disturb the waveform. So it is preferable that your waveform should not have a DC, let us say, voltage, or you should not have a DC component. And if at all you need to check if your continuous time function has a DC component or not, then you can simply see the Fourier transform. So in the Fourier transform, whatever is the power at f equal to 0, what is the component at f equal to 0, represents the DC potential. So in all the above waveforms except for bipolar RZ and maybe Manchester as well, other waveforms have a DC level, and these two waveforms do not have that. So with the help of this, I think you can easily understand these graphs, which is, I think, given in Haken, and I would suggest that you go through the advantages and disadvantages given by Haken. I think they have just given it in a very small manner, in a very small, you can say, presentation on page 204 and 205. And they have also plotted these functions on the next page with the help of the expressions which we have derived in our, let us say, notes today. You will be able to understand it. Okay. So I think I can close at this point, and I will wish you all the best for your mid-sim. And if there is any, you can say, issue or anything you want to ask, you can just unmute and say, I am there online for another 5 to 10 minutes. Those who want to stay, they can. Those who want to leave, they can leave.